Hello, I'm Kiran. I'm a compiler engineer working at ARM Limited. I'm a member of the Flang community, primarily working on OpenMP support in Flang. In today's tutorial, I provide an introduction to the Flang frontend. What we have on the screen on the left-hand side is the high-level flow of the Flang compiler. The tutorial will follow this flow. We will go through each stage with examples. At the same time, we will not be covering everything because there is a lot to cover. We will not cover driver, runtime, or OpenMP, but we will try to cover all other stages. Flang has a traditional compiler flow. The traditional stages of pre-processing, parsing, semantic checks, and lowering to an IR. The Flang frontend lowers to LLVM IR, which is similar to Clang. But the difference with Clang is that Clang lowers from the abstract syntax tree to the LLVM IR, whereas Flang lowers from the parse-tree to a high-level IR called FIR. The FIR high-level IR is built using the MLIR compiler infrastructure. As people might know, MLIR interfaces with LLVM IR through the LLVM dialect. And FIR basically lowers to this LLVM dialect, and then the MLIR flow takes over and converts it into LLVM IR. So that's a very high-level overview or a high-level flow of the Flang compiler. Before we go into the details of the compiler, I have a quick Fortran introduction in case people are not so familiar with Fortran. Fortran is a language that is popular with the scientific and HPC community. It is the first commercially available general-purpose language. It first appeared in the 1950s at IBM. Fortran has great support for arrays and floating point numbers. And there is a lot of code that has been written over several decades. And this code continues to work. And the Fortran language is not a static language. Like C++, it has been developing over a period of time. It is a modern language with support for modules, object-oriented programming, and parallel features. The latest revision was in Fortran. It was in 2018, called the Fortran 2018 standard. And another revision is due next year. From the LLVM point of view, having a Fortran frontend for LLVM is important to be successful in HPC. On the other hand, a good high-quality open-source Fortran compiler with a permissive license can aid standardization. People can basically prototype the features that before they go into the standard. Also, the availability of a good Fortran compiler and tools can help the scientists write better code. So now we have a quick look at a few simple Fortran programs just to get a taste of it. Basically, in the tutorial, I show a lot of Fortran programs and show the parse-tree or the high-level IR corresponding to it. So it's good to have a bit of familiarity with Fortran. So what I have on the left-hand side is the traditional Hello World program. So a Fortran program basically starts with the program statements and ends with the end program statement. It can have a name as well. In this case, it's called main. And the body of this program basically is writing the hello world string to the screen. So it's not just the main program that Fortran has. It supports structured or procedural programming with two kinds of things. One is subroutines, and the other is functions. So the difference between functions and subroutines is that functions can return a value. So what we have on the right-hand side is a subroutine, and typically in Fortran, there is a separation between declaration or a specification section and an executable section. So the code on the right-hand side has, in red, shows the declaration section, which basically declares a variable called x with type real. And in the executable section, the value of 1 is assigned to x, and it's printed. So in Fortran, all the variables have to be declared at the top, and it does not allow mixing of declaration and executable code. So next we come to the fixed and free form format. So these are two different ways of writing Fortran code. So the older version is called fixed form. As I mentioned before, the Fortran language first came in around the 50s. And those kind of days, it was the punch card machine. So there was a strict requirement on what can appear in various columns. So in fixed form format, normal instructions have to appear in column 7 to 72. A C in the first column indicates a comment. Columns 1 to 5 can have labels, and column 6 is for indicating line continuation. So on the left-hand side, we have this program in fixed format. So you can see that the first first line, the first column of all the instructions is the 7th column except for the comment. But obviously, this kind of coding is not possible in today's world. It's very error prone. It's very tedious. People won't want to go to the 7th column to always start writing their code, and they don't want to count also which column is the code starting in. So we have the free form format, which is what people use nowadays. In this kind of format, there is no restriction that the executable code or the code in the program needs to start in any separate in any fixed column. There are also no restrictions on the line length of each line. So finally, we have Fortran modules. As programs became larger in Fortran, it became difficult to have this code only in subroutines and in programs. So modules provide a way of packaging code, right? So what we have on the left-hand side is a module declaration. So it declares a module called 1. It has a variable called counter declared there. It also contains a subroutine called incrementer, which if called, increments the value of the counter by 1. And this module can be made available in other places by using this module. So what we have on the right-hand side is a program, Fortran program, and it uses this module. Use1 will use this module, and it prints the value of the counter. Then it calls the subroutine incrementer from this module, and then it writes the value of the counter. So if you run this program, basically, you will get 0 followed by 1. So now let's come back to Flang, now that we have had a look at some simple Fortran programs. The first stage of most compilers is the pre-processing stage. So in Flang, what we have is a pre-scanner and a pre-processor working together. So the output of this stage is a form called the cooked source, which is a version of the source program, but which is normalized. By normalization, I mean here is that all the characters are converted to lowercase. It is in free form, so any fixed form files are converted to free form. Any file inclusion has happened. If there are some macros, they have been expanded. So basically, it's a very well-defined form of the source code, and doing this normalization early on means that the parser and the rest of the compiler need not worry about all these macros, uppercase, lowercase, free form, fixed form, and things like that. But one issue is that the source locations might have changed. The cooked source and the original source differs in line numbers and column numbers and all that. So there is some provenance also produced, which contains some maps from the cooked source to the original source, so that if the parser or some subsequent stage provides a message, they can be mapped back to the original source location. So this helps provide good debug and location information. So that's the pre-processing stage. So we have the first source and output example here. So what we have on the left-hand side is a Fortran source. It's in fixed format. There is a preprocessor defined where message is defined as hello world. And in this code, we print this message, print star, comma, message. So On the right hand side, I basically provided the command at the top, flang new -fc1-e- no reformat file.f. So that's the command that you have to use to produce the cooked character string. So we can see that all the extra spaces have been removed. The preprocessor defined message has been replaced. All the uppercase letters have been converted to lowercase. And this is what we call the cooked character string. So, it's all very normalized. So the stage after the pre-processing is the parsing stage. So that's what we get on to next. So in Flang, we have a recursive descent parser. The grammar is taken from the standard and suitably modified. Left recursion is removed. And Fortran or in Flang uses parser combinators to implement parsing. There are a lot of token parsers which parse various tokens. Then there are operations and functions to combine these parsers to parse more complicated things. The parser is written in a declarative style. So what we have on the right hand side is an example of how the parser is written. At the top, I have various declarations. So the first one is a declaration declaring two variables A and B and assigning them values 1 and 2. The second one is declaring an array of 3 and then initializing it with 1, 2, and 3. And the third line is a string declaration with size, where the size of the string is 10. So the Fortran standard says this in the type declaration statement. It says that a type declaration statement is a declaration type spec followed by an optional attribute spec followed by an entity declaration list. And what I have shown for the parser below is the entity declaration. So what we have in the Fortran standard is basically an entity declaration and the entity declaration basically contains an object name followed by an optional array spec, followed by an optional coarray spec, followed by an optional star and a character length, and followed by an optional initialization. And at the bottom, we will see what it looks like in the parser. So the parser is constructed for an entity declaration by parsing an object name, followed maybe by an array spec, maybe by a coarray spec, maybe followed by a star and a character length, and maybe followed by an initialization. So we can see that the parser looks mostly similar to the way the grammar is written. So the hope is that this will help even non-specialists to write parsers. So again, I show an example here. So what I have on the left-hand side is a Fortran source. There is a function called add. It takes in two arguments, x and y, both of them are integers, and produces a result called set, which is also an integer. And the operation that's performed inside is an addition. And what we have on the right-hand side is the parse-tree that is generated for this program. And at the top, I have provided the command for generating this parse-tree. That's flang new -fc1 and using the option debug dump parse-tree. So I provided matching colors for us to match, the source code to its corresponding, the corresponding entries in the parse-tree. So the things in red corresponds basically to the function. The thing in blue corresponds to the declaration section or the specification section where 3 variables x, y, and z are declared. And the execution statement, or the execution portion, corresponds to the place where the addition happens. So the stage after parsing is semantic checks. So semantic checks or semantic analysis basically checks that a given Fortran program conforms to the standard. All these checks are not possible in the parser because it requires additional information. So a lot of expression and statement semantic checks happen in the semantic checks. There is also labels in Fortran, so go-tos and names of constructs, like you can exit a construct. So these kind of names and go-to labels have to be checked. Also, another thing is that sometimes the parser can produce a parse tree that is ambiguous. So in this case, more information is needed to form the parse tree correctly. So in semantic checks, once the types and everything is known, you can modify the parse tree if you find that it's ambiguous. Constant expression evaluation also happens in this stage. And for Fortran modules, some representation of the module has to be generated. So that also happens in this stage. So the first example I have here on the left-hand side, it shows a subroutine. It has a select case statement, which is some way like the switch statement. And in this program, I have erroneously given a case, and in that case, I have passed in a real operand. But in Fortran, the select case expression cannot have real. So that's what is the error that we see on the right-hand side. Error, select case expression must be integer, logical, or character. And at the top, I have provided the command also, which can help provide this error. The next example I have is about rewriting the parse tree. So what I have on the left-hand side is the Fortran source, which basically declares an array called G. It has a few elements. And then I have two statements are there. The first one says f of I is I plus 1. So Fortran has something called a statement function. So statement functions are something like inline functions. So here f corresponds to a statement function. So that means that if I call it with f of 3, you will get back the value 4. So that's f of I is I plus 1. Whereas the thing that is appearing below, which is g of I is equal to I plus 2, is basically saying that add 2 to I and store that value in g of I, right? It's an array store operation, and it's not a statement function. But what we see in the middle column, where if you dump the parse tree without semantic checks, is that even g is passed in as a statement function. But once we reach semantic stage and we know that G is not a function, but G is an array, then in the semantic checks we can correct this parse tree to what is shown on the right hand side. So that there you have the execution part, and you see that it has been modified to an assignment statement, which is all shown in green. So the final example that I show for the parsing and semantic checks is the Flang module format. So as I mentioned before, some representation of the module has to be stored so that it can be used by wherever this module is used to check the data types and the function declarations. Different compilers do it different ways. Some compilers, have a binary format for module files. Some have some fixed and specified format for the module files. In Flang, what we have, where we store the source itself along with a header, and the header contains a magic string which denotes that it's a module file with a version number matches the version of the module file, and also a checksum to ensure that the contents of the modules are not changed. The body of the module will contain all the declarations of both the variables as well as the functions or subroutines. And when this module is used by some other portion in the source code, then the compiler can check whether the signature of the subroutines and functions match, whether the types of the variables that are used match. So that's what we have on the right hand side at the bottom, where I've given the module file corresponding to the source on the left hand side. So the next stage after parsing and semantic checks is the lowering from the Flang parse tree to the high level IR called FIR. So In this stage, basically we traverse over the parse tree, and at each of the leaf node, for each of the construct, for the Fortran construct, we generate the appropriate FIR code. But I'm not going to go into the details of this lowering stage. I go straight to the FIR representation. So as I mentioned before, FIR, or the Fortran IR, is built using the MLIR framework, which is part of the LLVM project. It contains types and operations which model the various Fortran constructs and entities. There are types for arrays, strings, structure-like derived types. There are also high-level operations for arrays, loops, select statements, and things like that. Before lowering to FIR, all names have to be unique, so that there are no clashes between the names that can appear in the IR. There are also a lot of transformation passes on FIR. These include simple things like constant sub-expression elimination. These are improvements over the basic MLIR constant sub-expression elimination. It also contains a lot of passes which simplifies higher level FIR operations and converts them to lower level operation. Coming to tools that can be used with FIR. So first of all, to generate FIR, we have to use the driver Flang new with the emit FIR option. And secondly, there is this tool FIR OPT, which can be used for performing MLIR related transformations. So the first construct and the operation corresponding to the construct that we are going to look at is the do loop. So before we get into that, I just want to make a quick distinction between two kinds of loops. The first is structured loops, and the second one is unstructured loops. So the loop in Fortran is called the do loop. It's similar to the C or C++ for loop. The representation is by do and end do, and there is a variable. There is a loop index variable, and then we say what is the start here? It is 1, and what is the end here? It is n. And on the loop in the left hand side, we basically increment the value of an accumulator called res with the value of the loop index variable. So the loop what we have on the left hand side is a structured loop. There are no unstructured constructs, or there are no statements like exit, go to, and things like that. These all will, if we have exits or breaks or continue or statements like that, they can potentially cause a branch instruction. So we don't allow any of them in the structured do loops. An example of an unstructured do loop is shown on the right hand side. So the difference on the right hand side is that it compares the variable res with 0, and if res is greater than 0, then it exits out of the loop. So this can cause a branch instruction, and such instructions are not permitted inside this loop. So the name of the operation which corresponds to the Fortran do loops is fir do loop. For people familiar with MLIR, it's similar to the SCF4 loop. So all structured Fortran do loops are converted to fir do loops. And for the purpose of optimizations, these loops, if possible, are converted to affine loops. For those Fortran loops which are not structured, the fir do loop is not created for them. For these kind of loops, a control flow graph is generated by using branch and similar instructions. So this slide shows an example of a simple do loop. So what I have on the left hand side is a function called sumN. It accepts an integer as argument n, and it returns a value called result res. Basically, this function has a do loop which iterates from 1 to n and accumulates the sum of the first n numbers from 1 to n. So I've used matching colors to match the representation on the left hand side and the right hand side, so that it's easy to go from the source code to the FIR code. So I'll go from top to bottom here. So in the purple color on the right hand side, we have defined %0 basically corresponds to the loop index variable I. In the orange color, we have the result variable allocated. In green color, we have the constant 1. What is shown in red color is the number n, which is the upper bound of the loop. And in light blue color, I have represented the start of the loop as well as the end of the loop. So this loop goes from 2 to 4. 2 corresponds to 1 and 4 corresponds to n. And inside the body of the loop, there is a fir load instruction that loads the value of result, and fir load %0, which loads the value of the loop index variable. And then an addition is performed, add I %9 and 10. And then the value of the addition is stored to %1, which is result. And this happens for the entire duration of the loop. And once we finish the loop, the value of result is loaded and returned. So this was a quick and simple example for a simple do loop in FIR. So next we come to something called array operations in Fortran. Fortran allows array expressions. The example that we have on the left-hand side basically shows the summation of two arrays. A is equal to B plus C, where A, B, and C are all arrays. So this is captured in FIR by a few operations. Array load, which loads an entire array into an SSA value. Array fetch, which fetches a particular element from that SSA value. Array update, which updates an SSA value, which updates a given SSA value with some particular value in a location and produces a new value. And array merge store, which can store back the updated array. So what we have on the right-hand side is the FIR generated for the array expression on the left-hand side. So again, I have used matching colors. What is shown with red is the array A. What is shown with green is the array B. And what is shown in blue is the array B. And what is shown in green is the array C. So you can see that there is this array load in red, which loads the array into the SSA value 3. Then there is this array load in blue, which loads the array value into 4. And then there is this green array load, which loads the array value C into 5. And then inside this do loop, an individual element from B is fetched, and an individual element from C is fetched, and an addition operation happens. And then this array update operation creates a new array value by updating the old array value. And finally, after this entire array is updated, you have this array merge store, which stores back this array to the original array reference for A, which is arg0. Now it's not just so the array expression operations might require insertion of a copy instruction. So that's what is shown in this example here. On the left hand side, we have a subroutine called assign. It takes in an integer A. It takes in an array integer A of size 4, and inside the subroutine, what happens is that we are taking the values of the array slice from 1 to 3 and storing it to the array slice 2 to 4. So assume that the contents of the array A are 1, 2, 3, and 4. If you don't copy the value of A into a temporary, and if you do this evaluation in a loop, what we will get is 1, 1, 1, 1, right? But if we instead copy this array value A into a temporary, and then do the second copy, then we will get back 1, 1, 2, 3. So what is expected in the standard is the latter. So Fortran array expression evaluation requires the insertion of a temporary. So this is handled in FIR by a pass called the array value copy pass. So what the array value copy pass does is that it looks at array values that are fetched and updated, and it checks if these refer to the same array. If it refers to the same array, but it happens to be coming from different shape, right, or different slices, then it's very likely that there is a conflict. And if a conflict is detected, a temporary is inserted. So that is one of the job of the array value copy pass. Besides this, it also replaces this array load, array fetch, array update, and array merge store with normal loads and stores. So that's what we show on this in this slide. So again, in red color, what we have is the array slice from 2 to 4. So we have C2 to C4 with step size of C1. That's what the slice denotes, and this is loaded into the SSA value 2. And in green we have the array slice from 1 to 3, and this is loaded into the SSA value 4. And inside this loop, you have the array fetch operation, which fetches from the slice from 1 to 3 and updates the slice from 2 to 4. And then if you run the array value copy pass, what it basically does is that all the array value operations like array load, array store, array fetch, and array updates, and array merge store are all replaced by normal loads and stores. And it achieves this by converting this into a sequence of 1, 2, and 3 loops. The first loop copies the value of the array A into a temporary, and the second loop copies the value of A of 1 to 3 to temp of 2 to 4, and the final copy basically takes the copies the temp array into array A. So what we have, because this is a lot of code, I'm not able to show all the things, but I have highlighted in green, and in green the slice from 1 to 3, and in blue color, I've highlighted the temporary array. So the last FIR constructs that we are going to look into is related to how we parse arrays. Fortran supports many kinds of arrays, and sometimes the shape of the array is not known at compile time. If the shape of the array is known at compile time, then these can be passed as reference to arrays, when calling a subroutine. But if the shape is not known at runtime, then an array descriptor or a flat pointer is needed. The fir.mbox operation creates this array descriptor. So what I have on the left-hand side is a subroutine called SB. It's calling a subroutine called ARR underscore sum internally, and the ARR underscore sum subroutine expects an argument ARR, which is an integer of basically size 100. So what we have on the right-hand side is the FIR corresponding to it. Basically, what this FIR shows is that a temporary, a local array was created for ARR1, which is of size 100. And then when you call this function ARR underscore sum, we just pass that array directly. Whereas in this example, when we are calling ARR sum expects an array, but that array can be of any extent. It has to be of rank 1, but it can be of any extent. And in this subroutine, what we are doing is we are passing an array, but its size is a parameter n, which is not known at compile time. It will only not be known at runtime. So what we have on the right-hand side is basically the code corresponding to this. So there is an alloc operation which allocates an array, but this array is not, its size is not known. What we have in light blue color is the argument n, which shows the extent of the array. And we created a shape object which is of n. And then using the mbox operation, we take the array and apply the shape and create a descriptor which is stored in the SSA value 4. And then it's this descriptor that's passed to the array sum function when it's called. And later on in the code that is generated for array sum, it can look into some fields in this descriptor to know its size and shape. So the next stage after we have FIR and we have done all the transformations in FIR is converting it into the LLVM dialect. So MLIR provides a systematic way of converting operations in one dialect to the other dialect. So what we have to do in MLIR is that for each FIR operation, we have to define a pattern that converts it into LLVM dialect operations. It has to be kept in mind that not all FIR operations are convertible to LLVM dialect. Some, like the FIR do loop, would have been converted to CFG operations by this time. Besides specifying the patterns, we have to specify which are the dialects or operations that are legal after conversion. In this case, it's simple because we are converting it to LLVM dialect. What is legal after conversion is the LLVM dialect operation. And then we have to convert, then we have to apply the conversion. So again, for this purpose, we have to use the FIR tool with the FIR to LLVM IR option. So in this code, what we have is basically whatever I've described before. There are various patterns that are inserted. So we'll look at the complex comparison pattern later on. And then we specify which is the legal dialect after conversion. In this case, it's the LLVM dialect. And then we apply all these patterns for conversion. So this example shows the conversion of a complex comparison operation into the LLVM dialect. So basically, what should appear in the LLVM dialect is that you take the real part of the complex number and then compare whether it's equal. You take the imaginary part of the complex number and see whether they are equal. And if both imaginary and real parts are equal, then return the result. So that's what is shown in the code on the right-hand side. And LLVM.AND is the final AND, does the comparison of both the comparisons of the real as well as the imaginary part. And this is achieved by this C++ code, where you can see that we create extract value operations for extracting the real portion, and then we create a comparison operation for comparing the real portion. And similarly, we do that for the imaginary part. And finally, we add an AND operation to do the AND of both the real and imaginary comparison. So the last step in the flow is to translate the LLVM dialect into the LLVM IR. So this is provided by the MLIR framework, and the tool to use here is to use bin MLIR translate with the MLIR to LLVM IR option. So that's what we had for today. I would also like to end by welcoming people who are interested in developing Flang. We have bi-weekly calls on Mondays and Wednesdays. I have provided a link where you can see details about these calls. We also have this Flang dev mailing list where you can mail and contact us. We also operate a Slack channel, flangcompilerslack.com. I provided the link through which you can get an invite to join us and talk to us. So that's all for today. Thank you.
Hello, everybody. Thanks for watching the tutorial. It's time for Q&A. If you have a question, please type it in and I'll read them out and we'll get an answer. We have one question so far. Ask if the FIR dialect is mostly complete or if it's missing some things. For example, can it handle allocatables, derived types, and combinations of those things?
Yeah, I think it can handle these kind of constructs like allocatables and derived types. So most of Fortran 95 is fully supported in the FIR dialect. There exist prototype versions of operations for Fortran 2003, but they're not complete. So things like the parameterized derived types, things like procedure pointers and all, they're not as at the moment fully supported. But everything else in the Fortran 95 standard and below is fully supported.
Okay. Someone asks, what is the difference and what improvements have been made in the descriptor format comparing classic Flang to F18?
I think I'm not the expert here, but F18 tries to be more compatible with the standard. So in the Fortran standard, they have a descriptor for C and Fortran interfacing. And the descriptor standard, the descriptor format that is used for Flang is mostly based on that. So due to that, I'm of the opinion that it's more friendly to the standard and it's more conforming. And there is hope that because we are closely modeling what is in the Fortran standard, there might be opportunities for interfacing with other compilers.
Okay. Someone wants to know, why does the -E option on the driver require -FC1 as well? Because Clang doesn't require CC1.
Good question. I don't know what is exactly the reason from the top of my head. Maybe without the FC1 option also it works. But usually we have been using this FC1 option, so that's why I put it there, because FC1 handles all the developer options, and that's the one that I usually use. But I can check it up whether you don't actually need the FC1 option for -E.
Okay. So if you were to step back and look at all the work that's gone into Flang and think about what could be added to LLVM, what would you suggest?
That is a good question, and probably a bit out of my league. But I mean, LLVM is mostly, or LLVM started off as an IR, although it's independent of high-level languages or lower-level platforms. There is a bit of C baked into it, and also things like alias analysis and all are mostly not what we would want in Fortran. Like in Fortran, normally things don't alias. But whereas in C or C++, things alias. So we have some difficulty usually interfacing Fortran compilers with LLVM for this purpose. So that's one area where probably some improvements can be made. I think there is a lot of work that's going on there. I'm not fully following all those, but alias analysis or better way of handling alias analysis is something that LLVM can provide.
Okay. It sounds like Flang is very much a work in progress, and there's plenty of different things that people could volunteer for. Is that true? And how can people find out what's left to do, or how can they contribute?
Yeah, that's a very good question. So Flang is still a work in progress. We have been mostly following development in a standard by standard format, like we did Fortran 77. Now we are Fortran 95 compliant fully. But there's still a lot of work for Fortran 2003, Fortran 2008, and then Fortran is a living language, so there will be always new versions of standards. So there is always new work to do. That's one case. But there's also the other case that there are possibly a lot of optimization. FIR is basically high-level IR that's created so that people can easily write transformations to convert FIR to other dialects that are there in MLIR. So there's a lot of opportunity for a lot of work there. If you are interested, obviously you can contact us by writing to the mailing list. We are in the process of upstreaming all the remaining downstream code. A bit of downstream development has happened in a downstream branch. So all of that is being upstreamed into LLVM project. So once it is fully there will be actually more opportunities for people to contribute. But if you are interested in contributing now, please send us a mail. We can give you the right pointers.
Okay, we only have 45 seconds left, so make it quick. What do you think of MLIR, and how's your experience been so far?
I have been personally working on the OpenMP dialect with MLIR, but the regular or the core FIR team has been working on developing the FIR dialect with MLIR. My personal opinion is that it has been very pleasant. So it is a very useful utility. to write new operations, write new transformations. And it also looks very good, like, all the high-level information is captured there. So it looks much better than if you just look at the LLVM IR. So I've been happy using it.
All right. Thanks, everyone, for coming.
Thank you.